Record. Okay, the record is on. We don't have any question. So let us resume the problem. Okay. You can see that because we have the constant moment on the actual part in the second on this section, but that makes our life a lot easier because you can see that I can also begin my integration from here. It's the same origin here, same sign convention, and I don't have to do anything because on the second zone it becomes a constant value. Okay, and here I would begin from the right as well to avoid having another constant at the beginning. Okay, so from this now we can write our moment equations to set up our integrals. Okay, so let's say let's hope that I can keep this with me. So I'll have portion AB, the big M for the actual moment, that would be 20x. Okay, and the small m for the virtual, that would be just x. And range from 0 to 15. Oh, 15. I always, that's a bad habit of just not lifting your pen. Okay, 15. So is there any question about that? That should be as straightforward as it gets. Okay. So the next portion, I shouldn't be moving this much. Okay. The second portion, BC. You can see that the moment for the actual case becomes constant. So it's 300. So 300 is true, you know, regardless of any distance. So that will sort of free us to use the same equation here. But you now must be mindful that if you want to maintain this equation, the range for integration must be from 15 to 30. So this is going to be, you know, the pitfall for some of you. You know, the range here will be incorrect if you are not careful. Okay. See, this equation 1x is true throughout the length of the member. And because in the actual case, this becomes constant, so it really doesn't matter which range you use, just an integration of constant value. Okay. So now we're back to the last portion that we must get it done. That's a DC. And now some of you still cannot work from right to left. I don't know why. So if you want to work from left to right, this would be such a burden because say, let me then demonstrate to you that if you want to work from left to right, your moment equation would be 50. Oh, that's 300, not 50, right? 300 plus 50x minus the uniform rule is 4x squared over 2 instead. And this will be 30 minus x. So you have to, you know, carry out the work with these two moment equations. Think about that, 3 terms, 2 terms, but from right to left, now you have 2 terms and 1 term. So it's a lot easier. And when it is a lot easier, you are also less susceptible to making mistakes as well. So for DC, that actual case is going to be 70x minus, let me get rid of that right away. So it's x squared over 2. And for this, it's just another x. Now the range is from 0 to 30.
It's time to. It's time to not
Right.
divided by 2.
Oh, right. You're right. Wow. Wow. So that is the kind of mistakes that some of your friends make in the exam. 2x squared over 2. Thanks. Okay. So now be mindful that we are doing the virtual work. So you must collect all the work of the system. That means the integral of the entire system. So we're using virtual work method to calculate displacement. Delta D now becomes integral of 0 to 15. The actual load here is 20x multiplied by x dx over EI. Move on to portion BC. The integral will become this, right? 15 to 30. And the equation is 300 and x, actual and virtual, dx over EI. And the last one, let's hope that it can fit here. From 0 to 30, 70x minus 2x squared multiplied by x. Oops, let's not do that. Multiplied by x dx over EI. So if you've come to this point, you know, the calculator can do the dirty work for you. Or if you still have fun with the integration by hand, you can actually do it, but you have to, you know, have a high level of concentration, because you have to multiply this first and then you integrate the whole thing. So you have to integrate 20x squared. So that's how you get 20x cubed over 3 EI, right? From 0 to 15 plus, right now it's 300x. So it becomes 300x squared over 2 EI. From 15 to 30, be mindful again, this range you have to have 2 values and then, you know, subtract them. And then this, it's 70x squared, right? So it becomes 70x cubed. Oh, it looks like 3. I'm trying very hard to write properly. 3 EI x cubed over 3 EI minus 2x to the power 4 over 4 EI now. Okay. Okay, and this is from the whole thing is from 0 to 30. Okay, so you don't have to do this yourself, but I'm just doing it because I've done it before and because I still enjoy calculus. And just to show you that it's not really that difficult. The difficult thing is just to form your idea and write the moment equation with a proper range and origin. Okay, so in the end, this turns out to be, let me skip part, give you the number right away. 3, 4, 8, 750, and a beautiful number over EI. Okay, so that is the delta D, delta capital D, the displacement, horizontal displacement at D due to the actual load. Now, this is going to be the displacement at D due to the unit load or due to the reaction. But I don't use reaction. I don't want to write H in my integral, so I'll just use the unit one. So this, as I have said so many times, for this case, my actual load, remember it's this case, right? The second case here, this is my second case where I want to know the horizontal displacement at this location caused by this load. So this, because I want to use the load equal to 1 and I want to find out how much this load 1 will cause the horizontal displacement here. So this load becomes my actual load. And because I use the virtual work method, so I apply the unit load to solve the displacement of the actual load, which is 1. So in this case, the actual load and virtual load are incidentally equal. And therefore, my integral will be this. Now remember, because of the virtual case, this is in fact the same equation. So I can, wrap them up, because there is a formula in calculus saying that if the function is the same, just to remind you, the integration of fxab plus bc fx is in fact equal to integral from a to c. You remember that kind of thing? Okay, so that is leading us to the, the wrapping up of two integrals into just one. Look like 330, and my actual load is x. My virtual load is also x dx over ei plus another equation which just looks the same. In order to avoid your confusion, let me write another integral that looks just the same, so that you know this one represents member CD. Okay, but I might as well multiply by 2 now, because they are the same. So it's 2 integrals x squared. So that comes out to be x cubed over 3ei, and range is from 0 to 30, and that gives us beautiful number of 18,000 over ei. Again, you can see that if you've come this far, you are 70% already. So yeah, let's go back here. Now, step number 5 is to establish compatibility. And now we have delta D plus delta DD, because delta DD is caused by the unit load. So the displacement caused by the reaction HD must be the one caused by the unit load multiplied by HD itself. And then when they sum them, when they are sum up together, the result must be 0 because of compatibility and because of our actual structure has no displacement at D. Okay. So now we just, assemble them. Now we have 3, 4, 8, 7, 5, 0 over ei plus 18,000 over ei multiplied by HD equal to 0. So now you get your HD equals minus 19.375 kilonewton. Again, this minus sign means HD is opposite. Is in opposite direction of the unit load. Okay. So if I don't ask anymore, which I generally don't because it takes a long time to write the shear force diagram and bending moment diagram of your structure. So it is say, not a good idea to ask you to do it again in limited time. But let me show you something. After we've got to this point, now remember you have two cases like this, right? This is the case of the actual load. This is the case of the virtual load. Now you know your reaction is 19.375. So when you calculate the reaction of the entire structure again, you don't have to go back and apply 19.375 there, because now you have this. You have the reaction of this load case, right? Come on, okay, yep. Which is 20, 50, and 70. Now you can add this if you believe in superposition. Now you have this. Remember what you have done before is this, right? To the right and then up like this. This is the force that you apply at the first time, and then you got this reaction. But then you got the result here of minus 19.375. If you believe in linear elastic, just like what we have done, you can easily use this result to calculate the reaction, the rest of the reaction right away. If these numbers are the reactions caused by this unit load here, now that I know my HD is 19.375, but in the opposite direction, I can easily use this to calculate reaction right away, right? Now that I know this is in fact 19.375. If that is 1, this is 1, and if that's 19, so this is 19 as well, but in the opposite direction because of the sign. And if that is 1, gives me this 1. Okay, if this is 19, it should give me another 19 here as well. But the direction is opposite. And then the last one is the same. Or maybe I should write this again, because this comes from this, right? We have this. And that everything is 1. So if this becomes minus 19.375, this would become minus 19.375, this would become minus 19.375, this would become minus 19.375. Okay, and in the end, the reactions you just sum them up. First case and then this case. And then you can easily get the reaction of the entire structure. Okay. This is 20 and then 19 in the opposite direction. So in the end, this is only 0.625. This is 50 up plus 19 more. So this becomes 69.375. This one's 70 up but 19 down. So in the end, that is 50.625. And then we have 19.375. If you believe in superposition, this is done very easily. Again, you don't have to do this, but you know, many students like this and kind of make you guys look cool, you know. So you can do this, or you can just, you know, apply 19.375 back to the original structure and then recalculate the reactions. But again, you don't have to do it. Okay. And after you get this, I still have a page to go. So from here, I can now, let me try to write this 4 kilonewton per meter. You can also draw your shear force diagram and bending moment diagram very easily. And so for the first piece, $69.375. Oh, okay. .625. That is 20. So now you know that has to be 19.375, right? And then we are going to have the moment here that is going to be equal to, let's use the pink one. The moment is equal to 20 multiplied by 15 minus 0.625 multiplied by 30. That is, do I have the number? 281.2. Okay. And let's go on. Well, let's do it properly, because I have told you many times that you should complete the step first. And some of you did not listen and try to draw shear force and bending moment diagram. There is no proof that you can actually achieve the complete free body diagram of the system. I told you, and then you didn't listen. Okay. So the second piece, this one, moment is 281.2. And now we have 50.625. Now, because this one is going up, so this one comes down with the equal amount of number. So this one goes up 69.375. And then you have the uniform load. And then the moment of 281.2. So that is another free body diagram complete. You can check by take the moment. Okay. So let's do that now. So let's say if I look, if my eyes are here, and I prefer that. So my shear force diagram will be like this. Okay, so that is 0.625, minus 19.375. And again, because this is the positive area, so you should have the, oops, okay. The positive moment value here equal to the area of this. That is, the moment here is equal to 0.625 multiplied by 15, which is only 9.4. And then this negative area should bring your moment down to the negative value of 281.2. Okay, this comes from 9.4 minus 19.375 multiplied by 15. Okay, and the point of inflection in this case would be easy because you have just the point load. So the point of inflection here is just 0.625 x minus 20 x minus 15, right? This is the moment equation, and then set them up equal to 0, you get your x. Okay, now let's move on to the second one. This, oops, I have to erase this. Okay, it's the same thing. Shear force diagram to be simple enough. 69 is greater than 50, so you would expect the triangle on top to be slightly larger than at the bottom, right? 69.375 and then minus 50.625. Then your moment diagram should begin with a negative value because of the presence, because of the presence of the negative moment at joint C. Okay, so this will come down to be minus 281.2. This is number. Then again, the positive shear area here would bring your moment up. Whether or not it will reach positive value, you have to do some calculation, and it appears to be the case. And then this negative area should and must bring your positive value down to 0 again. Okay, so and this distance here is 12.66. All right, is there any question? You can also calculate this positive moment by using the pink area right away. It's easier, but you always should check every time you have the opportunity. Okay, so the moment here, you can use the pink area to calculate. It's going to be a half of 12.66 multiplied by 50.65 or minus 281.2 plus the brown area, a half of 30 minus 12.66. That's the base of the triangle, right? Multiplied by 69.375. Okay, so then that's it. And if you want to calculate point of inflection, it's easier to do it from the right. So it's going to be the moment, which is equal to 0 at this point, is equal to 50.625 x minus 4x squared over 2. Okay. Any question? That's it. And I have the number here. Because this is just a simple equation, because you can eliminate 1x, so x is just going to be 25.3 meters. Is there any question? Yes, it's minus because you mean this one, right? It's minus because it's a negative moment, you see?
No, you go up, teacher, because you write go up. Yes, in the bending moment you write in the up you see bending moment.
Yeah.
You write into
Yeah.
x1.2
And
because wait a minute, teacher.
Well, it's a number, right? But yeah.
Okay.
So it's 281.2. This the number the same, but I didn't write any sign. Maybe if you want, it's it's the negative value. Just add it. Okay.
Okay, teacher.
Okay. Thanks. Is there any more question?
Can you go up again?
Okay. Sorry.
Up. This page. Okay, thank you.
Okay. You okay now?
It's okay, but I want to write a little bit. Okay,
sure. Take your time. Let me give you a minute or two. Catch your breath. So you have one more equation, one more example. Oh, you know what? Let me go in the strands of my hair in the dustbin. You know what, you guys, junior, next steel class should be my last steel class. So if some of you just do it and have to drop the class, be mindful that you take the class again. I will not be there. Maybe it's a good thing. Okay, because Ajahn will take full control of the class again. It's his class. I'm just a substitute to help him out while he is the head of the department. I think he is no longer the head today. Okay? I shouldn't say that in the record, but it doesn't hurt anyone. It's a fact anyway. All right. Is there any question regarding this example? No. Okay. So as much as I want to give you a break, we still have like 15 minutes to go. So let us try to establish the last example, and we can come back after the break and finish it. I don't wish to start the next topic today, even if we finish earlier. So, because your mind will collapse possibly. So let us carry on and see what happens. Okay. All right. That's another one. It just give you this crazy looking frame. And the benefit of this online class is that you get to see a lot more examples because things go faster. So, okay. This one is kind of fun. I haven't used it a long time ago. It's good to use it here today so that it can be recorded, it can be visited in the future as well. So you can see now we have a sort of a prop cantilever structure, but this time it is a frame. So Again, you can have your two choices. After step number one, of course, we can determine that this is the 1 degree of redundancy structure. You may remove the moment, or you may remove the roller here. Okay. Generally, I prefer to remove the roller, but I don't know why. When I look at my notes, actually it's the moment that I remove. So let me write this for you. If you face something like this, you can have a choice to create your primary structure that looks like this, right? Or you can just remove the roller altogether and have, oops, like this, structure like this. So either way should give you the same result in the end. So I don't think any choice will be much more difficult than the other. So it up to your preference now. Okay. So let's say that's step number one. We determine the degree of redundancy, and therefore step number two, we are going to create our primary structure. But it's good that I will establish the first case, because now you get to see how we deal with this moment. Okay. So our primary structure, I have decided to remove. Let's give it some name. Okay. A, B, C, and D. So I'd say I remove MA. So when you remove the reaction that is moment, now you're going to have rotation. Okay. So our primary structure becomes this one. Now. And now I am going to have this as a consequence. I will have theta A. And this is, oops, that's not 1, that's 50. Why did I write 1? That's 50. Okay, so this is the actual case, actual load case. And now this is another primary structure presented with the unit moment. Okay, this is the virtual case. Is there any questions so far? I hope not. So you better be careful with the reactions and so. Okay. So.
Excuse me.
Yes.
As far as I've seen all the problem, you use the direction of the removed force to be opposite as the probably.
It doesn't really matter, you know.
Yeah. I just wonder if can you show if we use the I think they probably.
I think this is going to be the opposite, because you mean the same?
Yes.
Okay, because we can expect this moment to be this, right?
Yes, I just want to.
Okay, sure. Why not? No problem. I'm just gonna, in the end, I'm just gonna swap the sign, So no problem. Okay. Roger that. Why not? Okay. So this time, but you have to help me now, because I may commit some blunder. It's fine. So now we're going to, I just want to use the same color. So let me go and revisit this. Let me see how I did it. First problem. Okay, it's a pink one. Okay. Now it's a brown one. Okay, so this time I am going to apply the unit moment here. And now I will have perhaps the rotation theta A. Okay, so the next step is to analyze this in the actual case. It's 50. Now we have this, and then we have that. So you can easily take the moment, you know. This is going to be 40. And that is going to be 10. Okay, and for this, if we now apply 1, you know, this is practically a couple, right? And you can see the distance here. Now we have the clockwise moment, so I better have the counterclockwise reaction, right? So now you get your wish, or the direction of the forces will be opposite, which for the sake of demonstration, it's okay, but you don't have to try to find yourself some trouble, you know what I mean? Okay, it just maybe if you, to me, the direction doesn't really matter as long as I can write my moment equation very easily. Because for the sake of demonstration, you probably can see now that you will have to struggle with the direction of the forces and so and so, because they are just running in the opposite direction. But in the end, I guess it doesn't really matter to me, and it should not really matter to you. What matters most is you must be consistent with the sign convention that you use. If you use one sign convention for your actual case, you must use the same or the similar sign convention with the virtual case. Be consistent. That is the most important thing. Okay, so let's say go back to the structure. Now this is 4 meters. That's 4, but that's 3. So that means this oops, sorry, last step. This distance is in fact 1 meter. So this is actually, it's somewhat just like you're dealing with a 5 meter long beam. Okay, so the couple has a distance 5 meters apart. So that means this has to be 1/5, right? And then that's 1/5. Any problem with that? Okay. Another thing that you must be mindful is that, look at this. This direction is not perpendicular to the member, and neither is this one. So when you write the moment equation for virtual work, you must use it. You must use the force perpendicular to the member, okay, with the x that is the true length of the member. I cannot vouch 100% for sure that if, let's say, if you are going to use the moment equation like this and then use x like that, you know, theoretically it's correct, but then if you use x like this and then a force like that to write the moment equation, you will not get the correct moment diagram, even though the end moment will be correct, but you will not get the proper moment diagram on the member. And so neither the proper work on the virtual work. So be mindful of that. Your moment equation must be based on this actual length and actual moment at the location, at each location of the beam. You cannot use the direction perpendicular to this force, then use x from, say, this to that, from 0 to 3 to write your moment equation, because that will not give you the proper work of the member. Okay, so let us carry on, at least try to finish this Compatibility diagram. Now we have 10 here. We have 50 here. So you would know that the moment at the end, that is 80 minus 200. So that's coming down to 120, right? Again, you don't really need this value, but it would help you if you could. And your bending moment diagram would look like this. And when you can see the shape of the bending moment diagram, you now know that, well, we're not as lucky as the previous problem where we have the portion with constant moment. Now you have this equation, and then you have that equation. So two equations for this member, okay? And then we can look at the same time at this member. Now we have 1 here, and then we have 1/5 there. So the moment diagram here would be oops, that's a negative moment. And then should be something like this. Okay, and that's a straight line, that's one equation. But because the moment diagram of the actual load case breaks into two portions, so if you can write the diagram, you can see that you need two equations here. And then the leg portion, this one, member CD, you have this, and you have that moment 120, and then you have this sort of alien load. Okay, so you must use the trigonometry. That's the angle. This is the angle. They're the same, right? So this basically is what's the reaction? 40 cosine theta. And that is cosine. Where's the cosine? Let's work it ourselves, okay? If that is my angle, if that is 3, yeah, sorry, actually that must, I'm sorry, this is my fault. Let's this must be 4 meters from the original, because I kind of prefer 3, 4, 5 triangle. This is 4, not 5. So please correct that. Okay, so this is 4, so that's 5. So it's a 3, 4, 5 triangle. So cosine is 3/5. Okay. So that is 40 multiplied by 3/5. 60% of that. and that is equal to 24, I believe. Yeah. You must use this one because this is the perpendicular to the member, and the true length is x u to 5. Okay, and we can do the same for this. That's 1/5 multiplied by 8. So it's 1.6 minus 1. So here is the moment here is 0.6. Okay. So if that's 0.6 going counterclockwise, so this is clockwise, 0.6. We have 1/5 coming down. So the trigonometry would lead us to 1/5 multiplied by 3/5. That is 1/5 multiplied by 3/5. So you got 3/25. Okay. And now x is the same from up to 5. Okay. So we are pretty much ready for that. Okay. So I think it's a good time to take a break again. But since this is the second break, so let us have 15 minutes now. Okay. Do you have any question? Let me stop the record first.